All right, so get this. Billions and billions of planets. Just let that sink in for a moment. We're talking about our galaxy, the Milky Way, with something like 200 billion stars, right?
And the current thinking is that most, if not all, of those stars have multiple planets swinging around them.
Meaning we're talking about a mind-boggling number of potential worlds out there.
It's pretty wild when you consider the sheer scale of it all. I mean, while the idea of zipping between these exoplanets is super exciting, the reality is that the distances involved, trillions and trillions of miles, make it practically impossible.
Yeah, with our current understanding of physics, at least actually going to these faraway places is pure science fiction.
For sure.
So, okay, if we can't physically get to these planets, these other worlds, how do we even start to explore them? That's where light comes in. It's like our cosmic passport.
It really is. Light carries so much information about where it's been in its journey across space.
And if we crack the code, so to speak, it could even tell us about potential signs of life, on those distant planets.
And if we take a step back and think about it, you, our listener, with your interest in life beyond Earth, well, you're part of something truly massive.
We're talking a huge interdisciplinary quest, right?
Exactly. We've got biologists studying the incredible diversity of life here on Earth, geologists analyzing how different types of planets form, and then there are computer scientists modeling planetary conditions, even folks looking back at Earth's own history.
It all ties together, really, this idea of understanding the full spectrum of possible worlds out there. I mean, from the most vibrant to the totally barren.
Yeah, that's the beauty of it.
And for this deep dive, we're zeroing in on Dr. Lisa Kaltenegger and her book, Alien Earths. She's the director of the Carl Sagan Institute at Cornell, a real trailblazer in the field. She's doing amazing work modeling habitable planets, figuring out what those telltale light signatures might look like.
Which brings us to the big question. What's the mission of this deep dive? What are we setting out to do?
Well, basically, we're going to tackle the big one. Is there life beyond Earth? And we'll do it based on the best scientific knowledge we have right now.
Right, and that involves looking at how many planets are actually out there, the challenges of actually detecting life. I mean, what even is life?
Yeah.
And what makes a planet potentially habitable? Plus, we'll look at the current state of the search.
Yeah, lots to unpack. So, if the universe is potentially teeming with life, there's a pretty obvious question that pops up.
Yeah, where is everyone?
Right,
Yeah.
exactly. It's a question that's puzzled a lot of brilliant minds for a long time. I mean, it's not like we've had any confirmed alien visitors knocking on our door, have we?
Our source addresses this head-on, actually, even referencing Carl Sagan's The Demon-Haunted World.
Oh, interesting.
Sagan cautioned against leaning too heavily on UFO sightings. Those kinds of claims, well, they often raise more questions about us than they do about potential extraterrestrial visitors.
Yeah, true. If you think about the logistics, it does seem a bit far-fetched. Aliens zipping across the galaxy just to peek at us, using technology that's somehow invisible, yet also prone to crashing.
Right.
Something. But even in intro astronomy classes, the source mentions, students come up with some pretty thought-provoking possibilities for this great silence.
Yeah, you hear theories that advanced civilizations might accidentally wipe themselves out before they figure out interstellar communication.
Right.
Or maybe, and this one's a bit more sobering, maybe Earth is the exception, like the only planet where life ever got a foothold.
This whole puzzle, this contradiction between the potential for life and the lack of hard proof, it's not new, right?
No, it's not.
The source brings up Enrico Fermi, the famous physicist. Back in 1950, he famously asked, "Where is everybody?"
It's such a simple question, but it cuts to the core of the issue.
Totally. If technological civilizations are common, shouldn't we have picked up some kind of sign, some whispers, something by now?
And it's interesting to consider the historical context, too. Our source points out that Fermi was asking this question when the world was really grappling with nuclear weapons.
Oh, right.
That whole idea of a civilization developing the ability to destroy itself, it definitely cast a shadow over discussions about how long advanced societies could actually survive.
So the Fermi Paradox isn't just some abstract cosmic riddle.
No, it forces us to think about the potential limitations of any advanced civilization, including our own.
It's a bit unsettling, really, when you think about it. It makes you wonder about our own trajectory. Now, switching gears a bit, how do scientists even begin to estimate our odds of picking up a signal, out there in the cosmos? Our source talks about the work of Frank Drake. He was a real pioneer in the search for extraterrestrial intelligence, or SETI.
And what Drake did was develop this framework back in the 1960s. It's known as the Drake equation. It's not an equation that you solve in the traditional sense.
Then,
It's more like a structured way of thinking about all the different factors that could determine how many communicative civilizations are out there in the Milky Way.
and the source breaks down those 7 factors, right? It starts with how many stars are forming in our galaxy, and then what percentage of those stars have planets.
Then it narrows it down further what fraction of those planets could actually support life.
Good.
And then it gets even more uncertain. What are the odds of life actually starting on a habitable planet? And of those life forms, how many might evolve intelligence? And then even fewer, how many might develop technology for interstellar communication?
Wow. That's a lot of unknowns.
It is. And as the source points out, that last factor, the average lifespan of a technological civilization, that's the big wild card.
That's the one that could really swing things, right?
Exactly. On the one hand, you can be super optimistic and imagine long-lived societies, communicating across the stars. But then there's the flip side. What if civilizations tend to destroy themselves not long after developing powerful technology?
Right, that's the less optimistic view.
Definitely. But even with all the unknowns, the Drake equation is valuable. It highlights how incredibly complex the search for extraterrestrial intelligence really is. All those hurdles that might have to be overcome for contact to actually happen.
Yeah, it's a lot to consider. Now, when we talk about these distant stars and their potential planets, it's easy to lose sight of how incredibly vast space is. Our source offers a cool way to picture this, actually.
Yeah, the idea is to shrink our whole solar system, from the sun all the way out to Neptune down to the size of a 2-inch cookie. It gives you a real sense of how empty space is.
A 2-inch cookie.
Hmm.
Okay, I like that. Now, on that scale, how far away would our nearest star neighbor be? We're talking about Proxima Centauri. Would it be like a few cookies away? Maybe a playful?
Way, way further. Our source says it would be nearly 9,000 cookies away. Think of it as 4 football fields, lined up end to end, all on that same tiny scale.
That's wild. I mean, that's hard to even wrap your head around.
It is.
And to even start to understand these cosmic distances, miles and kilometers, they just don't cut it, right? That's where the idea of the light year comes in.
And light travels so incredibly fast. We're talking 186,000 miles per second or 300,000 kilometers per second.
That's mind-blowing.
It is. In a single year, light travels an unbelievable 6 trillion miles. That's 9 trillion kilometers. That massive distance, that's what we call a light year.
To help us grasp this, the source gives us some examples. Light from the moon, it takes about 1 second to reach Earth. Light from the sun, about 8 minutes. But light from Proxima Centauri, our closest star neighbor, takes over 4 years to reach us.
So a light year isn't just about distance, it's also about time, because light takes time to travel. If we look at a star that's, say, 50 light years away, we're seeing it as it was 50 years ago.
So we're looking back in time.
Exactly. It's like a cosmic time machine.
That's wow. All right, let's go back to the Fermi Paradox for a minute, to this great silence. Our source explores some potential explanations. One that comes up is this idea of technological self-destruction.
Right, like maybe advanced civilizations develop technology so powerful that they end up wiping themselves out before they can even send messages to the stars.
Oh, yeah, that's not good.
The source gives examples like nuclear weapons or even runaway climate change as potential cataclysmic filters. These things that could happen in a civilization's past, or maybe even more worryingly, in their future.
It's a sobering thought. It's like the very things that could allow us to connect with other worlds might also be the things that destroy us.
For sure.
But our source also brings up a possibility that's maybe a bit less dramatic, but equally likely.
Uh-huh.
What if our assumption that a civilization capable of contacting us would contact us is wrong?
Right. Why assume they even want to contact us
Yeah.
or that they do it right away? It's a very human-centered view.
Yeah, totally.
Or maybe interstellar communication is a very long-term project for them.
Oh.
Or maybe they've got totally different priorities that we can't even imagine.
Who knows? And then there's the basic challenge of communication itself.
Yeah.
I like how Source explains this. They use the analogy of trying to chat with a jellyfish.
Yeah, even here on Earth, communication between different species can be really tricky. And we're talking about organisms that are right in front of us,
Right, right.
Now imagine trying to bridge that gap across light years with a civilization that could be totally alien to us, biologically speaking. Different senses, maybe a completely different way of understanding the universe.
So even if they are out there sending out signals, we might not even recognize them as signals.
Exactly. Or even if we do, we might not have a clue how to decode them. It's like trying to read a book written in a language you've never seen before.
Makes sense. So if we want to even think about interstellar communication, we probably need some shared understanding of how the universe works, right?
Absolutely.
Which brings us to science and particularly math. Our source makes a good point. Throughout history, we've tried to understand the universe in lots of different ways.
From philosophy to religion.
Yeah, all sorts of ways. But the scientific method, with its focus on evidence, on testing things well, that's turned out to be the best way we know of to figure out things like, how planets move or how electromagnetic radiation works.
And it's that approach, that evidence-based approach, that underpins Carl Sagan's famous statement, extraordinary claims require extraordinary evidence. The idea that there's alien life out there, that's an extraordinary claim.
Huge, yeah. So it needs rock-solid proof to back it up.
Exactly.
Our source also talks about math as being the language that reveals the mysteries of the cosmos. Math is universal, right? It doesn't matter where you are in the universe. A mathematical principle discovered here on Earth would still hold true on a planet billions of light years away.
Right, and that universality of math is super important for how we model and understand these distant planets. Scientists use computer code to create simulations.
Yeah, like those cool visualizations you see in documentaries.
Yeah, those are based on mathematical models. Scientists plug in the numbers, stuff like heat, moisture, gravity, all to figure out if a planet could even support life.
It's like creating these hypothetical worlds in a computer.
Exactly.
But let's say we can't decipher alien radio signals. What then? Our source brings up another possibility, biosignatures.
And it starts with our own planet. If we look at Earth from space, our atmosphere has a specific mix of gases that, scientifically speaking, can only be explained by life being present.
It's like our planet is saying, hey, life's here.
Right. It's like a planetary fingerprint.
Yeah.
So by analyzing the light passing through a distant planet's atmosphere, we might be able to spot similar, unusual gas combinations.
And that would be a pretty big clue.
It would. It's a chance to search for other life forms out there, even if they aren't sending out radio signals or trying to get in touch.
It's like a more passive search, right?
Yeah.
Okay, speaking of sending messages, our source talks about the Voyager Golden Records.
Oh, yeah. Those are fascinating.
It's like a message in a bottle, launched into space, right? Back in 1977, they were sent out on the Voyager 1 and Voyager 2 spacecraft. Each record has this inscription: to the makers of music, all worlds, all times. It's pretty amazing when you think about it.
It really is. It's a time capsule meant to tell any intelligent life out there about what life is like on Earth.
Our source gives a rundown of what's actually on the records. There are images of life on our planet, different kinds of music from all over the world and throughout history, sounds of nature like the wind and rain, even greetings spoken in 55 different languages. It's a huge project. Carl Sagan and Anne Druyan spearheaded it.
Trying to boil down what it means to be human into a few sounds and images, that's a massive undertaking.
It really makes you think, doesn't it? What would we choose to share if we could send a similar message today? What would we want other beings to know about us, about what it's like to be human in the 21st century? It's a question worth pondering.
Absolutely.
But back to the records themselves. The fact that they're physical records is pretty interesting.
Yeah, the technology is almost ancient by today's standards.
The source mentions that both Voyager spacecraft carry a stylus and instructions on how to play the record.
Like a cosmic record player.
Exactly. But there's a point the source brings up that's really thought-provoking. The instructions specify that the record should be played at 3.6 seconds per rotation. But what exactly is an Earth second? It's arbitrary, right? It's based on our planet's rotation, which isn't a universal constant.
Other civilizations would likely have entirely different ways of measuring time. Trying to communicate something so basic as time, even with instructions, it highlights how challenging it would be to bridge that gap between our understanding and theirs.
So much could get lost in translation, so to speak.
Yeah, it really makes you think.
But even with those challenges, those records represent something incredibly hopeful. The source quotes Anne Druyan. She says, "Voyager moves among the stars. It keeps us alive."
It's like, in a way, those records are preserving our story, our hopes and dreams within this vast cosmic record.
Carl Sagan also had a beautiful way of putting it. He said that launching this bottle into the cosmic ocean is something very hopeful about life on this planet, even if it never reaches its intended recipient.
There's something poetic about that, isn't there?
It really is. All right, so sticking with the Voyager mission, our source talks about another powerful moment, the pale blue dot photograph.
Oh, yes. This is an iconic image.
Before Voyager 1 went off on its final journey out of our solar system, Carl Sagan convinced NASA to turn the spacecraft's camera back towards Earth one last time. They took the picture on Valentine's Day, 1990.
It's become such a powerful image. It shows Earth as this tiny, tiny point of light.
Sagan called it a mote of dust suspended in a sunbeam.
It's a perspective shift, isn't it?
Absolutely. The source points out how this single image captures the beauty and fragility of our planet. Everything, all of human history, all of life as we know it, is contained within that little speck of light. And the source reminds us how thin our atmosphere really is. Most of it is within just 6 miles of the surface. Imagine Earth shrunk down to the size of an apple.
Right.
Our atmosphere would be thinner than the apple's skin.
It's a powerful visual.
It makes you realize how important it is to protect this thin layer that makes life possible.
The pale blue dot, it's a reminder that we're all connected and that our planet is truly precious. It adds another layer to this quest to find other habitable worlds.
Now let's shift gears a bit and think about what it actually takes for a planet to be habitable. Our source paints a picture of the very early Earth, and it wasn't pretty. They describe it as a nightmare world.
Yeah, very different from what we see today. There were huge oceans of molten magma, constant bombardment by space rocks, and the atmosphere, well, it was mostly water vapor, nitrogen and carbon dioxide. Not exactly a welcoming mix for humans.
Definitely not.
And the moon, as we know it, wasn't even there yet. The constellations would have looked completely different. It's hard to even imagine.
I know. It really highlights how much our planet has changed over billions of years. The source then introduces gravity as this powerful force. They call it the most influential architect of the cosmos.
And it's true. Gravity was key to the formation of both stars and planets. It was gravity that pulled together those initial clouds of gas and dust.
Okay.
And at the core of stars, the immense pressure from gravity triggers nuclear fusion.
That's the process that powers the sun, right?
Exactly. The famous equation, Imensi-Shaw, describes this. It's the conversion of a small amount of mass into a huge amount of energy.
And that tiny conversion, that's what keeps us warm and makes life on Earth possible. The source mentions that the sun loses about 5 million tons of mass every single second. I don't even have words.
It's a mind-boggling amount of energy.
It is.
And when you look at how planetary systems form, well, the planets in our solar system all orbit the sun in roughly the same plane, and they all go in the same direction. This suggests that they all came from the same rotating disk of gas and dust around the young sun. Astronomers call these planetary nurseries.
Oh, fascinating. So how do planets actually form from that disk?
Well, it's a process called accretion. Basically, tiny dust grains start sticking together, forming pebbles.
Okay.
And over time, those pebbles become bigger rocks, then boulders, and eventually planets. This whole process can take tens of millions, even hundreds of millions of years.
Wow. So what about the different types of planets? We've got rocky planets and gas giants.
Yeah, and the temperature gradient in those early solar systems played a big role in that. Close to the hot young star, only heavier materials could withstand the heat, so that's where the rocky planets formed: Earth, Venus, Mars. But farther out, beyond what's called the ice line, where it was cold enough for water ice and other volatiles to remain solid, that's where you get the gas giants like Jupiter and Saturn.
And Jupiter is just huge. Our source says that all the other planets in our solar system could fit inside it. That's insane. I mean, what are the conditions like on these gas giants?
They're extreme, that's for sure. But as fascinating as gas giants are, the source brings us back to Earth, which is the biggest rocky planet.
Okay.
And it holds the biggest mystery because it's the only world we know of that's teeming with life, billions of different life forms.
All right, so back to that early nightmare Earth. How did it turn into the habitable planet we know and love today?
Well, it wasn't a quick process. For a long time, Earth was bombarded by asteroids and comets.
So like a constant cosmic barrage.
Pretty much. These impacts melted the surface and reshaped it again and again.
Oh, wow.
But they weren't all bad. The source talks about meteor showers, those shooting stars we see. They're actually tiny pieces of debris from this early bombardment burning up in our atmosphere.
Huh. So even those beautiful meteor showers are a reminder of this chaotic past.
Yeah, in a way. And of course, some of those space rocks did make it to the surface. We see the craters they left behind.
Like those really famous ones, right?
Exactly, like Alinde and Canyon Diablo.
Amazing.
It's cool to think that those meteorites are tangible pieces of the early solar system. They tell us about the building blocks of planets, including Earth. And when we look up at the night sky, we're seeing light from stars and galaxies that's taken a long time to reach us.
Because light travels at a finite speed, right?
Exactly. So we're seeing those objects as they were in the past.
It's like our own personal time machine. Now, what about the stars themselves?
Well, Inside stars like our sun, nuclear fusion is happening. Lighter elements are being converted into heavier ones.
Like a giant cosmic furnace.
Exactly. And this process can create elements all the way up to iron. It's what makes stars shine.
Okay.
But it's not forever. Eventually, our sun will run out of hydrogen fuel and turn into a red giant star. It won't explode as a supernova, though. Yeah, that's reserved for the more massive stars. They end their lives in these incredibly powerful explosions, supernovas.
And those explosions are important too, right?
Extremely. Supernovas are like cosmic gardeners, seeding the universe with heavier elements that are essential for life.
Really?
Yeah, things like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are the building blocks of all life we know of.
So we're literally made of star stuff.
In a way, yeah. Those elements are forged in the hearts of dying stars and then scattered across the galaxy. They become part of new stars, new planets, and potentially new life. It's a beautiful cycle.
So it's not just about finding the right kind of planet, but also about having the right ingredients.
Yeah.
Our source talks about the importance of an atmosphere for habitability. And they use Venus as an example, right?
Yeah, Venus and Earth are pretty similar in size and mass. At first, scientists thought Venus might be habitable. Yeah, but it turns out it's more like a hot hell. It's got this incredibly dense atmosphere that's mostly carbon dioxide, which creates a runaway greenhouse effect. The surface temperatures are hot enough to melt lead.
Yikes. So it's not just about being the right distance from a star.
Right, there's a delicate balance. Some carbon dioxide is good. It helps trap heat and keeps a planet warm. The source mentions that it actually warms Earth by about 60 degrees Fahrenheit.
Okay, that makes sense.
But too much carbon dioxide and things can get out of control.
Yeah, a runaway greenhouse effect doesn't sound good.
Definitely not. So there's this concept called the habitable zone, sometimes called the Goldilocks zone. It's that just right region around a star where temperatures would allow for liquid water to exist on a planet's surface. In our solar system, it extends roughly from Venus out to just beyond Mars.
So Earth is smack dab in the middle.
Right in the sweet spot.
Nice. But our source also points out that just being in the habitable zone doesn't guarantee a planet will be habitable. Venus was likely in that zone early on, but it got too hot and dry.
Yeah.
Mars is further out, but it got too cold and dry because its core cooled down.
And this highlights how important a molten core and active plate tectonics are. Earth has them, but Mars and Venus don't. On Earth, plate tectonics plays a big role in regulating the amount of carbon dioxide in our atmosphere over long periods. It's like a planetary thermostat.
Okay, that's interesting. I've never thought of it like that.
It's all about balance. Volcanoes release carbon dioxide into the atmosphere, and then the weathering of rocks removes it.
So it's a natural cycle.
Exactly. But Mars, being smaller, cooled down faster, its core solidified, and volcanic activity stopped. So the planet gradually got colder, and Venus... Well, it seems like the lack of liquid water was a key factor. Any early oceans probably evaporated.
Right.
And the water vapor rose up into the atmosphere where it was broken apart by ultraviolet radiation from the sun.
So the water was lost.
Yeah, basically. The lighter hydrogen atoms escaped into space. And without liquid water to dissolve carbon dioxide and remove it from the atmosphere, well, you get a runaway greenhouse effect.
It's amazing how many different factors have to come together to create a habitable world. Our source also talks about the role of a moon.
Right. Yeah, they mention the Earth-Moon system and its tidal effects.
Okay.
And how Earth's day length is very, very gradually increasing over time. The moon is also slowly moving away from us.
Fascinating.
It is. They point out that a moon can influence tides and might even stabilize a planet's tilt, which affects the seasons. But the big question is, would a planet need a moon to be habitable? And how many moons could a planet even have?
Interesting questions.
Right.
And then there's the whole thing with plate tectonics.
Yeah.
Our source mentions how Earth's continents look like puzzle pieces that could fit together.
That was the observation that led Alfred Wegener to propose the theory of continental drift.
But people didn't believe him at first, right?
Not really, no.
Yeah, it was a radical idea.
It was. But then, in the mid-20th century, scientists discovered seafloor spreading and subduction zones. We're talking about sonar and seismometers. Those technologies gave us the evidence to support continental drift, and that led to our understanding of plate tectonics.
Amazing how technology can change our understanding of the world.
It really is.
And earthquakes, those are often a direct result of these tectonic plates moving and bumping into each other.
Exactly.
And over Earth's history, the movement of those plates has created supercontinents like Pangaea and mountain ranges. It's pretty wild.
It is. Our source even mentions that they've found fossilized seashells high up on Mount Everest, which shows just how much the Earth's surface has shifted and changed over millions of years.
Wow. So those continents are still on the move.
Very slowly, yes.
Now, this all ties into the emergence of life, right? The source mentions how early life arose billions of years ago in all sorts of environments, shaped by these geological forces.
Right, from warm, shallow ponds to those deep-sea vents.
That's incredible. But then, what is life? It seems like a simple question, but it's actually really hard to define, isn't it?
It is. Our source points out how some of the obvious things we might think of, like movement or reproduction, don't really work.
So,
Well, fire moves, but it's not alive. Computer viruses can evolve and replicate, but they're not considered living things. And sterile mules, well, they can't reproduce, but we still consider them living organisms.
okay, so it's more complicated than it seems.
Yeah, there's not one definition that everyone agrees on.
The source brings up Paul Nurse, a biologist, and his 3 guiding principles for defining life.
Right.
1, the ability to evolve through natural selection. 2, existence as bounded physical entities. And 3, functioning as complex chemical, physical, and informational machines.
And NASA has their own working definition. They say life is a self-sustaining chemical system capable of Darwinian evolution.
Okay, that's a mouthful. But the source makes a good point. These different definitions are trying to capture the essence of life as we know it.
Exactly. But they're also trying to be open-minded enough to include possible life forms that might be totally different from anything we've ever seen.
And to understand how life might have begun, the source mentions the famous Miller-Urey experiment.
Right. That showed how organic molecules, the basic building blocks of life, could spontaneously form under conditions that probably existed on early Earth.
Fascinating. But our source is careful to point out that we're only seeing planets as they are now, not as they were billions of years ago.
Right, when life might have first emerged.
So it's a bit like trying to solve a puzzle with only half the pieces.
In a way, yeah.
But by studying different planets at different stages, maybe we can start to piece things together. What about the fossil record?
Well, here on Earth, fossils tell us that life appeared around 3.5 billion years ago. But finding evidence of even older life is really tough, because Earth's crust gets recycled through plate tectonics.
Oh, right.
And those delicate soft tissues of early organisms, they don't fossilize well. It's hard to find evidence of them.
So there's a whole lot of Earth's early history that we might never know about.
Probably. The source also talks about the Cambrian explosion, which happened about 530 million years ago. It was like a burst of evolutionary innovation, tons of new animal life appearing. Many of them had hard shells that fossilized more easily, so we have a much clearer picture of that time period.
Okay, that makes sense. And then, of course, there's Darwin's theory of evolution and the discovery of DNA by Watson and Crick. Those were huge breakthroughs.
Absolutely. Understanding how life evolves and the basic building blocks of life, those are crucial for thinking about what might be possible in other worlds, even if those life forms are completely unlike anything we've ever seen.
So the first life on Earth was single-celled organisms, right?
Yeah, they were the pioneers. And they ruled the planet for an incredibly long time, about 2.5 billion years.
That's a really long time.
It is, and they might seem simple, just a single cell enclosed by a membrane with the genetic code inside.
But they're the foundation of everything.
Exactly. And even though they're just one cell, they come in all sorts of shapes and sizes.
Oh, really? I thought they were all pretty much the same.
No, there's a surprising amount of variety.
And then there's that pivotal moment, the emergence of cyanobacteria.
Yeah, they changed everything.
They were the ones that figured out how to use sunlight and water for